Hello everyone, my name is Joanna Chi and I am from Simon Fraser University. Today I will be presenting DZIG, Sparsity-Aware Incremental Processing of Streaming Graphs. This is a joint work done with my lab mate Mugilan Mariappan and our advisor Keval Vora. Graphs are a flexible data structure that can be used to easily represent a variety of data and are applicable to many situations. We can use graphs to represent social networks, roads, and even disease transmissions. With these varied applications, graphs can also be very large in size, with millions of vertices and billions of edges. As a result, it is important to have systems that can scalably and efficiently process large graph data. Graphs are also dynamic and they naturally evolve over time as the data changes and grows. So we have streaming graph processing, where graph computations are run continuously in order to provide results that reflect the current state of the graph. For these graphs, being able to return results in a timely manner is important, as stale results may no longer be useful. So as time continues, the graph receives more and more updates via a continuous stream of graph mutations. And then the query results are computed on the latest result of the graph, which contains all the previous updates. Thus, it is important to be able to compute results at a low latency. To provide timely results, streaming graph processing uses incremental processing that reuses work that has already been done before, so that it does not redo the same work again. This means, as updates are performed on the graph structure, the computed results are incrementally refined to reflect the impact of these updates. The goal of incremental processing is to reuse the work that has previously been completed, so that processing will only be done on vertices that are affected by the graph changes. Graphbone is a state-of-the-art streaming graph processing system that does incremental processing to quickly compute final results that are fully correct. This means the final results are the same as if you were to perform a from-scratch BSP execution on the updated graph snapshot. Graphbone tracks dependencies in form of intermediate vertex values as computation progresses, and then it performs dependency-driven incremental refinement that incrementally adjusts these tracked values. So let me quickly explain Graphbone's dependency-driven incremental refinement. Basically, we first identify the change in vertex values that happen as a result of graph mutations, and then we propagate these value changes to the outgoing neighbors in a stepwise fashion across iterations. In this example, we have the vertices u, v, and w, and I am showing how their values change across consecutive iterations, from iteration k to iteration k plus 3. The colors represent the values of vertices that are computed by the algorithm. So if the color is different across consecutive iterations, for example u here, going from maroon to red, then that means the value of u is different in those two iterations. So now, the whole point is to incrementally adjust these values when the graph gets updated. This is done by propagating changes or differences in values that result from the graph update. So here, first u and w receive changes from the updated graph and calculate new values for themselves, and then, because their values change, they push their changes to v during the next iteration. And then, based on these changes, v calculates its new value. Now during this iteration, u and w once again receive new values from their neighbors, and so they recompute the results and once again push their values to v. This process continues iteratively till final results are computed. Now an interesting thing to observe here is what happens when the changes start diminishing and the values start to stabilize. So here, only w's value changes in iteration k plus 2, but u's value remains the same, which is shown by the same light yellow color here. So w sends this change to v, which is fine, but v's value at iteration k plus 3 is not aware of u's value from iteration k plus 1. So in order for v to calculate its value correctly, it still needs to continue pushing its value to v. So this is unnecessary work that needs to be done, which causes more values to be propagated even when changes have diminished and values have stabilized. The issue here is that the vertices do not retain the changes that they received in the previous iterations. So here, even if v had received this change in the previous iteration, it did not retain this change in the next iteration, which forces u to resend the value. Processing changes in this manner is not friendly to computation sparsity. So then this begs the question, how can we retain high-performance execution with dependency-driven incremental processing during sparse computations? To address this, we developed DZIG. DZIG is a sparsity-aware incremental refinement technique that uses dependency-driven incremental processing while retaining high efficiency in the presence of sparse computations. DZIG also follows the same philosophy of graph build, where dependencies are tracked as iterations progress, and the dependencies are then incrementally refined when the graph structure is mutated. So there are two things we need to figure out: how to identify sparse computations and how to retain computation sparsity as we perform incremental refinement. We first define sparse updates, which we call DelZero. DelZero is defined as the delta between a vertex's value across consecutive iterations. Basically, if the change in value, or delta, is less than the algorithm's applied epsilon, then that change is a DelZero. In our previous example, we can see that vertex u in iteration k plus 2 does not have a new value, so the delta for vertex u is a DelZero because there is no change, and hence, u does not need to push any value to v. These DelZeros are usually naturally expressed in graph algorithms to identify whether vertex values have stabilized. For example, in the PageRank algorithm, after the vertex value is computed, it is compared with the old value to see if the difference is above a threshold. This comparison directly determines whether the update is a DelZero or not. Now that we have identified sparse computations as DelZeros, let's see how we can retain them. We basically want to make sure that we express the computation in terms of changes across consecutive iterations. That is done by expressing incremental refinement in a recursive fashion. So in these equations, we want to compute gt of I, which are the dependencies for the updated graph, using gi values, which are the dependencies from the old graph. This happens recursively, which is captured from the delta ti minus 1 on the right side. Effectively, this means there is an implicit dependency between consecutive values of the same vertex, and this self-dependency retains the changes that were propagated up until the previous iteration. So then, we are only left with changes that happened in the previous iteration, and this is captured by the remaining terms in the equation. So first, there are the direct changes resulting from the edge mutations. For example here, a new edge from G to D is added, so that the old change needs to be propagated from G to D. Similarly, edge B to C is deleted, so we retract the old change that was propagated before the deletion. And then there are the transitive changes that trickle down from these direct changes. So for instance, as D's value changes significantly, the change is sent out to its out neighbors. Now, because all of these changes are based on the previous iteration, we can directly identify DelZeros, which is our sparse updates, and suppress them. And that is captured by the precondition on the operations here. Finally, going back to our original example, we can see that the vertexes u and w once again push their values if and only if their own values have changed. And we can also see that v maintains the change from the previous iteration. So when u's value remains the same, u's value is not sent again, and thus sparsity is retained in the computation. We have a formal proof of correctness, showing that results computed by our DelZero-Aware incremental refinement will always be consistent with the baseline VSP execution that starts from scratch. I won't be going through this proof here, but do check out our paper if you are interested. There are several other details present in DZIG that I won't be covering in this talk. I have presented the DelZero-Aware incremental refinement strategy in DZIG. We also have the adaptive sparse incremental processing that automatically limits the overheads of dependency-driven execution using performance monitoring, and a simple linear regression-based estimation strategy. There are also details about dependency tracking, our efficient dynamic data structure based on adjacency lists that enables fast graph mutation, and our programming model that exposes DelZeros to the runtime. All of these details are present in our paper. Coming to the evaluation, we thoroughly evaluated DZIG across different synchronous graph processing benchmarks: PageRank, belief propagation, collaborative filtering, code training expectation maximization, and label propagation. And we ran these algorithms on multiple input graphs, going all the way up to 6.6 billion edges. And we conducted the experiments on a 32-core server. Here, I am showing the execution times in seconds across different mutation batch sizes. So apart from a single edge mutation, we simultaneously applied multiple edge mutations, all the way up to 100 million edge mutations at a time. So we have resinc, which basically restarts the execution upon graph mutation and performs incremental computation. And we have DZIG, which significantly outperforms resinc as expected. DZIG's DelZero-Aware processing retains high performance even across very large mutation batch sizes. In fact, it pushes the scale of dependency-driven incremental refinement to over 10 million simultaneous mutations. And the consistent high performance delivered by DZIG is visible when compared with GraphBolt across different configurations. For instance, GraphBolt's dependency-driven execution works well for up to 1,000 to 1 million mutations depending on the graph algorithm. Finally, we compared the performance of DZIG with other streaming graph processing solutions, including Aspen, Graph1, Llama, and Stinger on PageRank and the shortest path benchmark. Since these systems focus only on graph mutation times, they do not have any incremental processing support, like GraphBolt or DZIG. So here, I am also showing the execution times separately for the graph mutation phase and the analytics phase. When it comes to end-to-end processing, incremental processing in the analytics phase is much more important than just graph mutation, and that is why DZIG and GraphBolt significantly outperform all of these systems. Specifically, end-to-end processing in DZIG is about 30 times faster than Aspen and is about 120 times faster than Graph1. For graph mutation times, DZIG's dynamic graph data structure enables fast graph mutation and is competitive in modern solutions. In fact, for a large number of simultaneous mutations, DZIG's data structure is much faster than recent works like Graph1. There are also plenty of other experiments that I haven't covered in my talk. For instance, we studied the performance across different degrees of sensitivity to changes and the memory consumption by our dependency tracking mechanism. I would highly encourage you to check out our paper for these details. To conclude, dependency-driven incremental processing is important to maintain high performance while processing streaming graphs, and GraphBolt already took a large step in this direction. DZIG takes the next big leap in pushing the scale of dependency-driven incremental processing to high mutation rates, and it does so using its DelZero-Aware incremental refinement strategy. DZIG also incorporates important techniques like adaptive incremental processing, merged edge updates, and efficient dynamic graph data structures that enable it to deliver high end-to-end performance and significantly outperform the state-of-the-art solutions. DZIG is implemented in GraphBolt as its core engine and is open sourced under the same GitHub repository. We invite you to check it out. Thank you!